So first of all, we need to understand where exactly the shear force will act. So naturally, whenever you are applying, the best example I can give you is take a sheet of paper. And when you try to tear the paper down, okay, what do you see? So you will apply tension in both the sides, okay, and then the crack will start from somewhere from the edges and the crack will propagate. So when you tear the paper, the crack propagates in with respect to the tension force that you apply. So similarly here also, the steel plates are being given with the tensile load and you are just putting one bolt in between. So what happens is the bolt may cut itself along the edges of the steel plates. Okay, so entirely different portions will come around. So shear plane is where the bolt cut itself. So here in this case, it is in between the two plates. So here, that's for single way shear and this is for double way shear. So when you look at these diagrams, then definitely you can say the first one, that is the single way shear, will apply for lap joint and the double way shear which will apply for butt joint. Okay, as for butt joint, two plates will be given with one or more cover plates and using that only the load will be distributed. So by using cover plates and you are providing two number of bolts, and here there are two levels at which the bolt can cut itself. So one is the entire plane below the top cover plate and the other one is above the bottom cover plate. So in two planes, the bolt can cut itself when the load is applied. So that is why here the number of shear plane is 2. Okay. So now you can understand what exactly is the shear failure of a bolt. Shear failure of the bolt is wherever the load is applied, because of the particular steel member that has been connected, it will drag the bolt along the side it is being pulled and the bolt will just fail according to the load. Okay. So either it is on double one-way shear or two-way shear. So based on the number of shear planes available for the bolt to fail. Okay. Next slide, please. Here we will see the different kinds of failure modes. Can you just zoom out, please? The slide is slightly zoomed in. Some details are not visible here. Yeah, thank you. Again, it's zoomed in. Thank you so much. Okay, so here the different kinds of failure modes of the bolted connection are there. So in somewhere the head will fail, in somewhere the shank portion will fail, in somewhere the threaded portion will fail. There is no surety that only this way the bolt will fail. No, based on type of loading behavior, based on all kinds of particular loading conditions, whether it is static load or dynamic load, based on that particular only we can say which type of failure can we expect in a particular bolted connection. Okay, so these are different kinds of failures. Next one, please. Next slide. So majorly of all the failure modes that can occur, the 5 major failure modes are there in the bolted connection. The first one is shear failure. So this is how the shear failure will occur. This is for one-way shear. The bolt may be divided into half. Okay, so this is only shear plane number 1. Next slide, please. So in two-way shear, please click somewhere. The animation will get active. So here, this is how the two-way shear acts. So the number of shear plane is 2, one above the bottom cover plate and one below the top cover plate. Okay, right. Please continue. Go to next slide, please. Next slide. Yeah, that's one. Sorry, go the previous one. Previous one. Yeah. So we have seen, no, next one, please. Yes, this one. Thank you. So we have seen the shear failure of the bolt and what is meant by bearing failure. So bearing failure is, So the load was unable to bear even both by load and also by the plate. And that is how the failure will occur. So that's the bearing failure. And next will be the tensile failure of the bolt. So that means the head portion or the shank portion or the threaded portion will just be pulled out by means of the excess loading that can come in. And next to this tension failure of the plate, here the bolt will remain intact. The plate will get failure because of the tension load. And the next one will be block shear failure. So to explain the block shear failure, I'll tell you a very easy concept. You would have seen the spiral booking, okay, spiral sheet bookings. And if you tear any one of the paper from that spiral, so what you may observe, so at the top, the first crack will happen on the paper, and after that, the portion of the paper that is left side of the spiral will continue to tear some away, and you will get a nice paper having half the diameter of the spiral bolt, spiral hole with you. Okay, so that means the portion that has been left out from the spiral on the other side, so that will exactly explain the concept of a block shear failure in steel. Okay, the same particular, you can see the image over here, block shear failure. So whenever the excess load that can come in, some portion of the entire steel member will just fail like a paper, okay, because of the load. That's how the failure modes. Next slide, please. Next slide, please. Yeah. So some images I have shown you. So over failure mode, overloading, the bolt has completely failed and it has been cut into half. And the next one will be fatigue failure, the second portion. So fatigue failure, this is how the cross section of the bolt will look. Why? Because of the repeated heating and cooling effect of a particular steel connection that can trigger this kind of bolt failure. And next will be galling failure mode. So galling failure means the thread of the particular bolt will get damaged. There will not be any thread at all. Okay, the thread will go out. So that's called as galling failure mode. And after that, the most important and the common one, corrosion. So here it is galvanic corrosion. So galvanic corrosion can be corrected in a number of ways, using magnetic protection or cathodic protection or by electrolysis process. So there are a number of processes are there. Okay. Next slide, please. So design considerations. So if you are going to provide number of bolts in a particular steel connection joint, what are the things that you need to consider? So the in-between spacing of the bolt rows that you need to consider, that's called as pitch. Pitch is called whenever along the direction of the load. And if it is perpendicular direction of the load, it is called as gauge. Okay, it's mentioned in G. And the edge distance E2 is given at the last bolt to the end of the structural steel member perpendicular to the direction, and the end distance is given along the direction of the force. Okay, and one more thing is there, staggered pitch, in which the loads are given in a zigzag way. So that can distribute the load even much faster way and also in a much better way, but mainly can be provided for inclined members or for members which are given at a particular angle for connecting members. So likewise, they can be given. Next, please. So this is the bolt clearance table. This has been given in IS 800. So it provides what number of size in mm that you need to provide for a particular bolt of a particular diameter. So definitely it needs to be larger than the bolt. Otherwise the bolt will not go in. Okay, so the nominal size either from 1 mm to 2 mm to 3 mm. So that kind of difference will be there. But majorly this difference is accounting for the thermal expansion of the bolt also. Okay, so that's why this difference in. Next slide, please. So bolt design check. Okay, so with respect to IS 800, if you're going to design a bolted connection, what are the checks that we need to do? First thing, we need to check for shear design check. Whether this bolt will withstand the shear force or not. Okay. Second one. Next, second will be whether this bolt will bear the total load for bearing failure or not. So that will be the bearing design check. Third will be tension check, whether the applied load will not give any tension on the bolt or not. If tension is provided on the bolt, whether the bolt will withstand tension or not. That's the tension check. Next one will be slip resistance check. So there is a particular formula in the IS 800 to calculate that. Next one will be combined shear and tension check. Okay, so in some cases or in particular load cases where you will get both the shear acting on the load and also the tension to act on the load. So whether your connection has been designed in a proper way or not. So that check is also there. So if you want to note it down, from page 73 to 77 fully comprises the entire details that you need to consider on a bolting design in structural steel or in majorly IS 800. Okay, you can look into it. Next slide, please. So now we are going to look at them. So what we are going to do is I'm going to have a angle member, ISA 100 cross 10 mm, which is given a 66 kilonewton tension. Okay. And what I'm going to do, this angle, I'm going to connect it to a gusset plate of 12 mm thick. Okay. Using HFFC bolted joint. So I'm going to assume the coefficient of friction as 0.5. So usually this value varies from 0.3 to 0.69 at the maximum. Okay, it will not go below 0.3 and it will not go more than 0.7. Okay, either you can somewhere you can assume it directly if it is not given, or if it is given, you can use it. So how we are going to provide? So let's look at the other slide. Next slide, please. So the formula we have already seen. The total F, that is tensile load that is acting is 66 kilonewton. It's given. So here I have given as N equal to 1. So can you guess what is N? N is the number of shear plane. Okay. So when you look at the cross section in the gusset plate or the cut section, so what you can see, one plate, the gusset plate will be there, and above that the angle section will come and sit. Okay. So this is typically that's of a lap joint, and on a lap joint only number of shearing plane is only 1, and that is why the N is 1 here. And mu is 0.5 and factor of safety is 1.25. Next slide, please. So we know the formula, F equal to N mu T by FOS. So all the values we know it except T. So T you can find out. Here it is 165 kilonewton. And based on this, I have assumed M14 bolts of 8.8 grade. So you can assume any bolt of market availability that you can design on your own choice. But based on which diameter you are going to adapt, you need to put the appropriate proof load for it to calculate how many bolts are required. So when you put that, the number of bolts required, that can come up here. Here it is coming, it has 2.39. So we cannot exactly put 2.39 bolt on a particular steel connection. Always round up the value to the nearest above number. So we are going to provide 3 numbers of M14 HFFC bolts of 8.8 grade. So as you can see in the particular image, the 3 bolts are being provided and the tension load is applied. Okay, so this is a very simple and a basic connection problem. Okay, next slide, please. Our steel connection is not limited to this, but also we have a load that has been applied eccentrically. Okay, eccentricity of the load will also play a major role, because in natural load distribution, not every load is axial. Okay, some eccentric load will also come. So if the load is eccentric, then what happens is every load will behave in specifically different. So with this figure, can anyone tell me which bolt will fail first? So I need your answer in the chat box. For connection taking shear and moment. Okay. So what is moment? The force applied, if it is from a distance to a particular point, that will create a torque. And because of that torque, the section will have a moment. Okay. So here the bolt will undergo shear. Also, the bolt will have to take moment. Okay, so in this bolt, you need to tell which bolt will fail first in this particular group of connection, right? I'll explain you when you have write down your answers at the last. Next slide, please. So the reaction on the bolt at the eccentric loading. So here, so you might have written your answers on the chat box, but anyways, I'll explain it to you. The extreme last bolt, either at the top or at the bottom, will experience the maximum force because of the eccentric loading. So the combined design of shear and also the moment, the last bolt will need to be first designed. If they are taking the load, then all the inside bolts will take the load. So that's how the condition is, because that's where the maximum force will be subjected. Next slide, please. So that was for shear and moment, and this one is for shear and tension. So what happens if we are giving a bolted connection like this, and if the load is applied on the top, so what happens is the bolts are subjected to shear, and also the bolts are being pulled along its length direction. Okay. So if that comes, what happens? So next slide, please. So this is how the particular member can behave. This video I have done in ANSYS. This is one of the finite element software models. So please click the animation. So with the bolt applied, sorry, with the load applied, that is the tension load applied towards the top. So see how the member is behaving. Can you show that one more time, please? Please click it one more time. Yeah, when the load is maximum, the member is just bending like this, okay, like a small hill, the bottom plate. So this phenomenon is called as prying, P-R-Y-I-N-G, prying. So what does this prying imply? Next slide, please. Next slide. So prying, this is the mathematical expression for prying. So what happens is whenever the tension force that been applied on a particular joint like this, the small hill-like appearance will appear on the connecting plate, which induces a certain extra force that needs to be provided on the bolted joints into consideration. And here it is mentioned as Q. And for calculating the Q value, this is the formula. So for all these beta, eta, and LV and LC, these are considered in the design purpose. But here I'm just telling you giving you the knowledge of how the steel structural load distributions can occur. Okay, so this value is called as prying, and here this prying load will be equally distributed on both the rows of the connecting member. Of all the bolts, the value will be equally shared. Next slide, please. So with this, I have given you the basic concept. The credits are given here, and the next slide is the reference. So the basic structural steel connection member on the bolted connection is I have discussed with you. And along with that, not just restricting to it, the other design methodologies and the load available structures and the loading conditions also we have discussed. And we have discussed the types of bolts and the particular type of bolt that we have discussed, and how the shear, different failure modes of a particular bolt, and how the different joints have been done on a particular connection. So all the things we have seen it. So hope this webinar gives you the good knowledge